Okay. All right. Can you see that okay now? Everything look good? Okay. All right. So we left off last time talking about specific heat and how specific heat is how quickly something heats or cools, i.e., how much heat it requires to actually raise the temperature of a given amount of substance. And so one of the things you may have noticed from that is that when you have very low specific heats, they heat up very quickly. They distribute that heat very fast. Okay. The other thing you may have noticed is when you have higher specific heats, they're going to take a lot of energy to warm up. Okay. And so, for example, water takes a tremendous amount of energy to get boiling, right? To get to that higher temperature. That's why water is a huge heat sink. That's also why, like, if you get to the coastal areas, they have more moderate temperatures. It's because they take up and release heat, a lot of the heat in that area. These states of matter, again, we have solid, liquid, gas. We already covered that. We did accuracy and precision. What was accuracy again? How close you are to the actual value, right? Okay. Excuse me. Precision is then how close your individual measurements are to each other, right? The typical demonstration of this is a dartboard. So if I have a dartboard, something like that, right? And I go 1, 2, 3, am I accurate or precise? So accuracy is going to be something like this would be accurate because it averages to the true value, right? So this one's going to be what? Precise. This one's accurate only, right? But not precise, is it? Because they're far apart. Okay. And what if I get all right next to the target? That's both. Okay. So that's accurate and precise. Okay. Accuracy can actually be really tricky if you don't already know what you're going to be looking at. Okay. Because you can be very precise, get a bunch of readings that are all very tightly grouped, and never recognize that you're just off completely, right? It'd be like if you only have one tape measure and the tape measure's wrong. You're going to have troubles, aren't you? Okay. Usually accuracy requires a lot of repetitions from different labs, different systems working. So these are some different ones: U.S. customary unit, the SI or metric equivalent, and U.S. customary equivalent unit. This is actually the conversion factors that go back and forth from the U.S. units to the SI or metric units. So when you read your lab reports, you will typically see these in a deciliter. And again, deciliter, deci, meaning decimal or decimate, 1/10, right, of a liter. Okay. And so that's actually the same thing as 100 milliliters as well. The other unit you'll see, because it's usually a millimole per deciliter on the top, or they may say millimole equivalents, which is MEQ, is you'll see the millimole. Now, we haven't talked about moles yet, and we'll talk about that in just actually next chapter. But millimole is 1,000th of a mole. Okay. And so that's 1,000th of a mole per every 100 milliliters of your blood or serum, depending on what they're talking about. So when you're talking about electrolytes, these actually use what's called milliequivalents. It's a slightly different thing. It's very, very similar to what we've just discussed right here. Okay. But the equivalents are actually a unit where it takes into account the charge of these things. For example, sodium has a +1 charge, whereas calcium has a +2 charge. And so if you have sodium and calcium, well, calcium actually counts twice as much as sodium, doesn't it? Because it would account for twice as much charge. Okay. So in your United States, the body weight is usually measured in pounds. Pharmaceuticals, however, are often dispensed by body weight in kilograms. Typically, hospitals tend to have like a program that kind of does it for people and checks them. But if those programs have and do go down, And then they have to sit there calculating out pound to kilogram conversions. Or they get a completely new drug, it's not in the system yet, and they have to do the calculations manually. Okay? So this is actually one of the reasons why this is actually nursing chemistry, is because I have had, at this point in my career, I've probably had 4 or 5 dozen people come up to me and go, Dr. Clausen, you teaching me those damn unit conversions? I hated them, but I saved somebody's life. Because I went, no, you can't give millimole quantities. You're supposed to give micromole. Don't give the person 1,000 times the dosage of morphine. That'll kill them. And so I have heard that just 4 or 5 dozen. I'm not sure which. I get stopped at like supermarkets by former students. And they're like, you're exactly right. Somebody tried to dose 1,000 times the dose. And I went, no, those are different. No, that's the wrong units. No. So this is calculating out a dosage. It's really just unit conversions, right? Dimensional analysis. You determine the units for the final answer, determine the given information, determine conversion factors to cancel units, set up the equation with given information and conversion factors, so your units cancel out, all except the final answer, right? Notice that's exactly what we did before. And it's really just the steps to solve any problem, isn't it? Yeah. So drop units, IV delivery of medications is oftentimes going to be measured in drops per milliliter. This is actually abbreviated GTT per milliliter. The abbreviation GTT is actually short for a Latin term, which is gutta, which means drop. This is actually somewhat falling out of favor, and I'm starting to see more and more where they just label a drop. Okay. And they have a very specific meaning, a drop, and they'll then address that specific meaning on the instruments now. Because this was just causing a lot of havoc because nobody speaks Latin, and even the doctors don't speak Latin very well anymore. The drop factor, this can be used to determine drip rates when prescribing volumes of medicine is required a given time period. So keep in mind how this is usually done is you'll have a drops per hour or drops per minute, and it'll literally count the number of drops that's going to be given to that person every hour or minute. Okay. And these drops are highly regulated, and the instrument has a very specific setup to actually measure a consistent drop. This flow rate is incredibly important. You can either kill someone or cause the drug to not have any effect at all if you get this wrong. Okay. The drop factors actually do vary with the diameter of IV tubing, and this is why specific instruments are going to very specifically address this usually. But if you have older instruments or you have instruments that haven't had proper maintenance over time, keep in mind these instruments very much can change as the diameter of your tubing changes. And so you can over and underdose people if you use instruments that are not maintained properly. That's why hospitals have very strict logging. If you ever go to a hospital and you don't see a log under, attached to the instrument, they're usually a clipboard that's hung on the instrument's back. If you don't see that, be very aware you probably have problems. Okay? There's almost certainly some sort of issue. Or if you see that and it hasn't been updated regularly, they're missing them, there's major problems. And it happens all the time. It's a very common medical malpractice. So it's actually a huge deal. Okay. In fact, I know 4 people that they misdosed and tried to give them one person 1 million times the amount of drug they were supposed to get. And it was a painkiller, so they would have suffocated to death. Yeah. The other person was 1,000 times. That was actually the morphine one. I know a person that was almost given 1,000 times the dose of morphine. So, yeah. Which would have really, really killed them very quickly. Okay. So let's talk about percentages in health. So the percent active ingredient. Now, because of the high potency of many medicines, binders are often going to be added to increase the size of the pill. Because just frankly speaking, if I asked you to measure out 1 grain of sand and apply a dose of 1 grain of sand, are you going to be successful in that? No, it's basically impossible, right? Manipulating that small amount reliably is almost impossible. Okay, it's very costly if you do try to. It gets even worse than that. Many active ingredients require such low dosing that it could be as little as like 2 molecules per each dose. It can be very, very, very tiny amounts. Okay, such tiny amounts you can't even see them, even with a microscope. Okay, and so that's why you get this big horse pill, and then the thing says on it, it's like micrograms amount of drug, right? Yeah, they had to dilute it so much just so they can manipulate it, right? That's just how bad it can get sometimes. That's also why the homeopathic medicines are almost always bullshit. Excuse me for the language. Yeah. Because if you actually look at what they're doing, they're giving you a dose where they don't know if there's 1 molecule of that substance in each batch. They have no idea because they're saying dosages they can't actually measure. Yeah. So most of those are actually like saline drops. That's it. Anyways, so the percent for of an adult dose, again, children weigh less than adults, so they are going to oftentimes be administered a percentage of a dose that's required for an adult. And so you'll have to administer a percent of that dosing depending on their body weight. It can be very small. And in fact, this is one of, has everybody heard of like the Segways? No? The guy that invented that also invented, those machines for like Coca-Cola where you can select what you want and it mixes it up for you? Okay. Same guy invented that. He actually made his money on pumps to deliver administrations for babies. Yeah. And so they're very, very accurate pumps that can administer these very tiny doses that baby needs, right? Because a baby's such a small fraction of a human mass. So it was actually before that, they used to kill babies all the time at hospitals because they'd give them way too much, way too little. It's very, very difficult to do. So kind of an interesting character if you ever look him up, by the way. Yeah, very cool character. So the percent and nutritional labels, obviously, you've all seen that on the back of your packages, hopefully. If you haven't, please look at some point, please. The nutritional labels list the amount of carbohydrate, protein, fat, as well as the percent daily value. This is going to show your contributions for a single serving or the suggested daily dietary requirements. They'll keep in mind those daily dietary requirements are based on one individual that's sort of an average person, according to what they thought, nutritionists thought at the time. The other part of this is that the carbohydrates, protein, and fat in the United States are actually the amounts that are added. They are not actually the amounts that are in the substance. Okay? This is notoriously true for any beverage that is fermented, like kombucha. The listed amount of sugar is actually vastly larger than the amount actually in kombucha. Okay? Beer is actually fairly accurate-ish. It would actually be more sugar than a soda if they listed it like they do for a soda. They actually get a special exemption for alcohol. The United States, right? Isn't that funny? Special exemption for nutritional labels for alcohol. Though it is funny because it does cause a lot of havoc in the U.S. If you ever look at U.S. nutritional labels versus European nutritional labels, they get to list what they think they made versus the U.S. that have to list exactly what they put into it. And so sugar ends up way overrepresented in the U.S. on our nutritional labels. And then all the Europeans think we way more sugar than we do. But yeah, we do eat way more carbohydrates than we need to. But the truth is that the reason Europe's thinner is usually because they have holidays. They're all about running down to the lake and jumping in it and swimming across it. We don't have anything like that here. And fat is really funny. Europe eats way more fat than we do. They are, yeah. Overall. So the HIV-1 virus particles seen in the photo below, and we see these right here, the little tiny green things, which is very small. It's on the order of 0.000000120 meters in diameter. Express this value using scientific notation and use an appropriate numerical prefix to modify the basic unit. So I want you to think about that for about a minute, and then I'm going to move on. But I want you to really give it an effort, okay? You may not be able to complete it, but really give it a try and find out where you're getting blocked, right? Yeah, so always try to give an honest effort on these things. Because otherwise you never find out what your problems are and you don't know, you don't get a chance to ask me. And there's no ability to improve then, right? This is one of those things, but at the end of the course, you're going to be like, this is super easy. But right now, some of you might struggle a bit. Okay, so this number is a lot less than 1, right? So we want to move that decimal place over until we're a number that's greater than 1, right? And then because it's a lot less than 1, we need to put a negative exponent on that 10, don't we? Okay? And so here's our number right here. We're going to move this decimal place, right there. And we have 1.20. Everybody say it okay? Notice our number is sig figs. It's the same, isn't it? Times 10. And then we have to put the power up here. Now, because we're moving this direction, we're making a smaller number into a larger number. This is going to be a negative exponent, because we need to represent that it's actually smaller, isn't it? And so we count the number of zeros, 1, 2, 3, 4, 5, 6, and then 7. Okay? So there is 7 decimal places we had to move this over, right? And so it's 10 to the negative 7. Does anybody have any questions about that part so far? Nope. Okay, so that's scientific notation for the meter. If you're going to go ahead and do this, then you really want this to be either in the micro or nano prefix, right? Either one of those would work. Okay, either one would work to some degree. They're not going to be perfect either way. Micro is going to leave you with a decimal place number. Nano is going to put like a hundreds number. Okay. In my experience, nano would actually be the more common one, unless you're planning on comparing this thing to like some other micro numbers. Okay? So if you're comparing it to like germs, you would use micro. If you're comparing it to other viruses, you'd use nano. Okay? These would be your numbers. And so this right here, this is going to be 0.12 micrometers. This one right here is going to be 120 nanometers. And notice all we did was we just did that same conversion as we looked at before, right? Okay. Does anybody have any questions about that? Did I lose anybody in there? Mm-hmm.
So both of those would be correct answers?
Yeah, they're both correct answers. Realistically, it's a flavoring issue at that point. What are you comparing it to?
I thought it was 1.2, so it's a negative 7. How does be right?
Yeah. And so what you're looking at is this is actually the change that we did. The you get it? That would be in the meters if you do that one. But so we have 0.12 because it was 10 to the negative 7, and we divided that by 10 to the negative 7.
Are these different problems?
Okay, so the first one is scientific notation in meters.
That's micro.
This is in meters.
Oh, okay. I thought you were like saying the other one was like the answer for the meters one.
Nope. This is the second part.
Okay.
And so this 0.120 is micrometers. Okay? And that's what that prefix is doing, right? It's moving over 10 to the negative 6 into that prefix. Okay? And this one nanometers is moving over 10 to the negative 9 into that prefix. Okay. Does that make sense?
Yeah.
Okay. So if you do the conversion, here, let's quickly do the conversion. Maybe that helps. 1.20 times 10 to the negative 7 meters is what we had. Okay. And then we do the conversion. We have meters. And you want nanometers or micrometers?
Micro.
Micrometers. And so what you can see here is for every 1 meter, there's 10 to the negative 6 micrometers. Oops. Oh, 10 to the 6, excuse me, micrometers. I did it upside down. All right. And so when you multiply these, do you know how to multiply exponents? Have you guys ever done that before? Okay.
I don't remember.
So the exponents here actually add together when you multiply. And so what you do is, that goes to 1, right? Okay. And so that's where you get the, yeah, we're doing this. Okay. And so that's where you get the 0.120 micrometers. Or 10 to the negative 1. Did that make sense?
Yeah.
And so you can see how you can use both methodologies. The using like micrometers just makes things a lot shorter, so you don't have to type out as much stuff, right? And it's easier to compare stuff. These are the study guides in case you're ever like, what did we cover in this chapter and what do I need to learn and go over? This, okay? You can just go back through these study guides and you can learn what each section should have covered, okay?
This is slideshow mechanics.
Yes. Yeah.
Where is it?
It is under these. If you go to that first landing page, about midway through, you'll see the slideshows as a link that you can download them from.
The first page.
Mm-hmm. So right when you land on Canvas, there's that page that has like my welcome information and stuff.
Oh, yeah.